Hey, I'm going to try and break down the CPU chip so you can understand it based on this diagram here into the different instructions and chips within this HDL. So firstly, we've got the in and out. So you can see here the instruction, the in-M, which is the RAM and the reset value. And the out, so we've got the out M, the value going to the M, the write, whether we write to it, and the address, what address we want to write that value to. And also the PC is what register, what ROM value we want to use. So I'll start with the NOT. So firstly, we get the 15th bit. That is the most significant bit, which decides whether this is a C instruction, A instruction. If it is a 1, then it is a C instruction, and therefore, so if this is a 1, then AN is, the A instruction is false. So this is not a instruction. This is not an A instruction. And then in here we reverse that again to get the C instruction, because if it's 1, it's not the other. So if this is true, this is false. Then this is true. This is false. This is true. This is true. False. So the first AND, we get the C instruction with this value here. So if this is a C instruction and the instruction 5th bit is true, which we can come back here. 5th bit 0, 1, 2, this middle one. If we go to the table, D. Oh, sorry, A, not that one. A. So if it is true, then we want to store the instruction in A. The next one is a MUX, so this decides, this is the one that goes before the A register. If so it gets the instruction and the output from the ALU, and using this ALU to A value, we then output the value from one of these two. The OR then takes in the A instruction. Is this an A instruction, or is the ALU going to A? So is this an A instruction? Yes, then store it in A. Is this a, are we actually getting the output MUX of A? Then yes, store it in A. They're the two times we'll actually want to store it. Otherwise, keep it the same. A register takes in this value. Is that what it is? And sorry, so yeah, so those decide whether we do want to store it and gives us this load value, and then use that load value to either store the input from MUX or keep it the same, and then we output whatever's in A out here, which will go to a few things. This MUX is the one that proceeds it. It takes in the A output, also the in M, so the M register. It also takes in the 12th bit of the instruction, which is the 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So A. So this is one of the deciding parts of the computation, so of which column we want to push in. And that then decides, so using that, we'll decide the AM out, which we'll use later. Is this that or that? And this takes, is this a C instruction? And is the instruction 4th bit true? Which we can say is the 0, 1, 2, 3, 4, which is, should be the D register. So if this is true, then we want to store this in the D register. Sorry, it's fine. So we can say, if this is the C instruction and the instruction 4th bit is 1, then store the value from the C instruction in the D register. Well, this is the deciding bit for it. This is the load for it. So then the ALU out comes into the D register, and this load D will then decide whether we store this in D or keep the current value. And then whatever that value is, we output it from the D register, which will go into the ALU. So here you can see the two. We have the D value and the A and M value, where is from that MUX. So these are the two values coming into the ALU, we have the ZX through the NO inputs, the 6th through 11th bits of the instruction, which we go from the diagram should be the comp section, so C1, C6. And they are then used along with obviously the ALU computational instructions to give us an output value, and these two values. So this is whether the output is a 0, and this is whether the output is a negative. It becomes important later. So after we've got these outputs, we've got an OR 16. So if the A out is valid, then we want to put that as the address M. So that's saying whatever the address is in the A register, we want to use that as the address we're going to store into the M register. The ALU out, so that's the output from the ALU. That's going to be whatever the value that we store. So that's the value that we store into the selected address here. And then if this is a C instruction and the instruction 3 is true, so that's the 3rd bit instruction, which we know is the M. Go along, it's the M value. So if it's true, then we do want to, this is the load bit, to say, all right, yes, write this value into this address. All right, so that stores in the M. Now we come down to here, this does the jumps. We have Z route, which is positive if the output was 0, and instruction 1, which is this jump here, which if we go down to the jump values, is the J2, which is the out equals 0. So if this is 1 and this is 1, we do want to jump. Then we make this jump equal to 0 true, or 1. This next one, NG out, is true if the value was a negative number. Instruction 2 is this J1, where the output is less than 0, so the negative. So if we've got this set to 1 in the instruction, and it is a negative number, then we want jump less than equal to true. Now, or Z route, and so this one just says, is the value 0 or less, which we then use here and invert it to positive, which then says, is this number greater than 0, which is obviously this right here. So now we go, the positive, is this greater than 0, and is instruction 0 equal to 1? So is this J3, which is out greater than 0? If we've set this bit to 1, and the value that's come out of the ALU is positive, then we want to set this jump greater than to 1, or positive, or false, or to true. Now, if the jump equal to 0 and the jump less than is true, then we can say that the jump less than or equal to is true. And then lastly, for these ones, if JLE, jump less than equal to, or jump greater than, is true. So in other words, if any of these are set to true, so if any of these are set to 1, then jump to A is a load bit we will use to decide whether we actually want to jump or output a register into the PC and store that value. If there's 0, then we don't jump at all, which so then and here, so if this is a C instruction, so because it's important, because you could have these ones, but in a number, so if you've got the A instruction, you could have you know, the first bit is obviously that's saying it's a C instruction, but you could have a number that's all 1s, so then it picks that up in these and says that it's actually a jump, but it's really not. So if the C instruction, if this is the C instruction and the jump to A is true, then we want to do the PC load, which comes in here, is true. On the bottom, we then reverse that for the PC increment, and I'll talk about that why after. So the PC, we have the inputs coming from the A register. We then firstly, if the reset is set to 1, then we reset the PC counter back to 0. Otherwise, if the PC load from the previous AND, so this one here, is 1, then save the register, so the A out, which is the value from the A register, into the PC. And that will then be used to get the whatever value that is from the ROM. Well, it always will be. And then lastly, if the PC increment is true, then increment the value in the PC. Otherwise, keep it the same. That's where, if you look at the actual PC chip, you can actually do this else. Out is equal to out, so it stays the same. But because we've done this PC load, this PC will either take in the A register or increment. It can't not do one of these, because otherwise your ROM will stay in the same position, which we can't have. And then whatever that is, it outputs to the PC, which is then used to get the next instruction. And that's basically how the CPU works and how this code does it. Cool, thanks.